Hi, everybody. So I went back to some of our old homework so I could show you how GeoGebra works. In the instructions, I did say, hey, you can use GeoGebra or the normal or the inverse normal calculator. And I actually had you calculate things by hand last time. So what I'm going to do is I'm actually going to show you the cool trick in GeoGebra where you don't have to calculate things by hand. So if you're in the distribution, you would use this to either calculate critical values, or you could build the sampling distribution and you could put your z-score in and you could calculate your p-value. So you could do either or with this, but what we're going to do is we're actually going to use not the distribution tab, but the statistics tab. And I know that you've used the statistics tab before when we were doing confidence interval. I told you that this had a confidence interval calculator in it, right? And those were the estimates. Well, now we're doing hypothesis tests. So look, we have all these tests, and these are actually your 5 tests. So when you do difference of this week, this is what you're going to want to use is your difference of means or your single mean t-test. So let's go ahead and actually do it with one of our old homework problems to see what we have. So we're going to borrow this one. So we're testing the claim that the proportion of people who own cats is larger than 20%. Our significance level is 1%, and the null and alternative hypothesis. So we know it's P, so larger than 20%. So that's not equal to 2%. That's a mu. This is a P. It's less than 0.2. That's a mu. That's a mu. Here's our P greater than 0.2%. Wow, it was really far down there, huh? And remember, you can always do it in pieces here on my open math to give yourself, make sure you're feeling right. Okay, so now that we know it's a one-tailed test, which direction? Look at that. As long as your variable for your population parameter is here on the left-hand side, you can see the direction the arrow is pointing on the alternative. It's pointing to the right. So this is a right-tailed test. Okay, and now what we're going to do is we're going to take our sample and we're going to throw it into GeoGebra. So this is a single proportion test. So let's go here. We're taking a test of a proportion, a single proportion test. We want to make sure I can't talk. We want to make sure that we are choosing the correct alternative. We had a greater than sign, so we're going to continue to use a greater than sign. Now here it says our sample is 700 people. So let's go ahead. We had a sample of 700 people. And now it says 21% owned cats. So let's go ahead and say 700 times 0.21. Oh, awesome. And so it knows that that's a success of 147. Sometimes GeoGebra can be a little bit finicky. Remember, this is classic GeoGebra. It's actually been really great this term, so it is not acting weird or finicky. Yay, I'm so glad when GeoGebra isn't doing that. The other thing I forgot was to put in a value for my null hypothesis. See where it's like, I don't know. It tells me how many successes. It tells me my N. It cannot calculate my Z. That is my test statistic, or my p-value. I know it's hard because we're doing a proportion. It's a capital P here to remind you that that's the p-value. This is exactly what you would be doing if you were running it in your TI-84. All right, let's go ahead then. And what was our null value? Well, that was this up here. So we're testing it against 20%. So we need to change this to 20%. We'll hit enter. I always kind of go through and hit enter. Sometimes I will just to double check, click on different alternatives to make sure that it's accepting all the information that I've given it. So here is this Z, this is my test statistic. So 0.6614, and I can put that in. The test statistic is 0.66 to 2 decimal places. There we go. And then my p-value, well, how cool is that? GeoGebra spits out the p-value. So it's 0.25. We'll hit submit. And you can see that is a huge p-value, right? That's 25%. So 25% of things of samples are larger than this sample. Well, that's a reasonable sample to get. And so we are going to fail to reject the null hypothesis because that's a reasonable sample to get, given that this is the assumption that we're given this assumption about the population. And so we will fail to reject our null hypothesis. Okay, so there is a single proportion or a single mean. What I'm going to do now is I'm going to go to our guided examples, and I scrolled down to the last one, the two independent samples. So this is our difference of two population means. So this is a mu1 minus a mu2. We're going to take a look. What is our question that we're asking? We're asking an interested citizen wants to know if Democratic US senators are older than Republican US senators. This is from a long time ago. This is from May 26th of 2013. So this is not going to hold up to today's standards. So when you are reporting on it, when you are creating your null and alternative hypothesis and you're creating your conclusion, remember that this is not about these senators now. We can only state these facts about the senators from 2013. All right, so what we're going to do is the mean age of 30 randomly selected Republican senators was 61 years and 247 days, or 61.675 years. Here's the standard deviation of that sample. The mean age of 30 randomly selected Democrat senators was this many years old, and here's the standard deviation from that sample. And then we want to know if this indicates that Democrats senators are older than Republicans. Now we can see, why did they ask that? Well, look, 61.7 versus 61.6. So just this alone, Democrats are slightly older than Republicans in this case. So we want to know, is that true? Does that hold up? Or should we say, that's so slight that they're basically the same age? So remember, when you're doing differences, you're asking, is there a difference, yes or no? So you are always going to have your null value be equal to 0. And if you go into Geogebra, and we're going to switch over to a difference of means, and remember, for us, I'm never going to let you have a z-test for your difference of means. It's always going to be a t-test because of the data that we're going to be working with. Now notice right here in the null hypothesis, there's our mu1 and our mu2 equals 0. Can you hear me typing? I can't change that. You cannot change that. Why? Because that is how differences are set up. That is how the difference hypothesis test is set up. We just want to know if Democrats are older than Republicans. Now, how do I set this up? Well, it depends on who is mu1 and who is mu2. So if I say mu1 is Democrats, then I'm asking if mu1 is greater than mu2. So subtract that mu2 over. Let me draw this out. I'm asking if mu1 is bigger than mu2, right? And you can see how when I subtract to make it look like this, that this is still going to be in there. If I had done it the other way around, if I had made Republicans be mu1 and Democrats be mu2, then I would have to flip my signage. It's all about the question that's being asked. That is one of the hard parts here. Okay, so let's go ahead and look at our sample. So we're going to put in our Republicans as 2. So 61.675. We'll go and hit copy, and there's their mean. Oops. All right. And then we need the standard deviation of 10.17 years. And then I need the sample size. So how many were I looking at? Oh, how many people was I looking at? I was looking at 30 senators. All right. And so there is my sample 2. Those are my Republican senators. If I go to my Democrat senators, the mean age, here's our average from our sample, 61.704. We're going to go ahead and copy that over. All right. And what is the standard deviation? Well, the Democrats had a slightly smaller standard deviation of 9.55. And then again, our sample was still 30. Now, because it's 2 different populations, right? We've split the senators into 2 populations of Democrats versus Republicans. There are other things, but that is just who we were curious about. So we're only looking at these two parts of that population. They did not have to have the same sample size. It's pretty common for people to contrive to have the same sample size, but that wasn't necessarily needed. Remember, for us, we are not dealing with pooled data. So you're always going to keep this pooled unchecked. You want unpooled data. You can read about that in the handout that I gave. All right. So double check that all your stuff is in there, your mean, your standard deviation, your N for sample 1, same thing for sample 2. Now this right here, this gives me my standard error. Why is my standard error? Oh, my standard error is 2.5. That's fine. Now look at how big my degrees of freedom are, 57.7. Every time we've calculated degrees of freedom up to this point, it's been really nice. It's been something like N-1 or N-2. All of a sudden, it's not very nice. And that is why I didn't give you the formula for it. I don't want you to have to calculate it. There are too many calculators out there working for you. So don't worry about calculating the degrees of freedom. You should write it down because this is a t-distribution. So we want to make sure that we're showcasing the fact that we are in a student t, because remember, they change. There's a different student t for every type of degree of freedom you have. And then here is our t. So this is our test statistic right here, 0.0114. Wow, that's like barely, you might as well just be on the mean at that point, right? You have barely gone away from the mean, because remember, that's how many deviations away you went. That's not really a deviation at all. This is why our p-value is almost 50%. Our p-value is 0.4955. This is a huge p-value. So we are definitely going to reject the null hypothesis. Anyways, this is really just about showcasing how to use this calculator. There are many different calculators out there. I personally love Geogebra because I think it's really nice to read and understand. I will say that you do need to be a little bit careful. So if you have a touch screen, I always find Geogebra is more finicky when you have a touch screen. If you don't have a touch screen, if you're working on a laptop like me, that's great. And that's just, I mean, that's fine. There are other things out there. TIs do the exact same thing. So if you have a Texas Instrument calculator, there's that. We have tons of tutorials for that. Let's see. The last thing I want to do is so that was our 2 independent samples. We are going to do a difference of paired means. So let's go ahead and copy this over into a fun blank. So, hold on, let's pause this video. Okay, so I just went ahead and I cleaned up the data and got it looking nice again. So we've got subjects A through H, and we have a before and an after. These are scores that indicate pain level. So the lower the score, the less pain this individual was indicating. And now they were given hypnotism, and so they were asked to score their pain level before hypnotism, and then they were asked to score their pain level after they went through hypnotism. And what we want to do is we want to know is, on average, did the hypnotism actually lower their pain level, right? That's what we're asking about. So whoops, I can get rid of this. So as we're looking at this, we want to say, well, what would that mean? So do I want to, whenever you're doing a, and we can tell that this is paired means because we're asking within an individual, did their pain decrease, right? So individual to individual, did something decrease? And that lets us know it's paired up data. So I don't really care about this before data, and I don't really care about this after data. What I care about is the difference of the 2 datas. And so we could do before, ooh, I can't type. Sorry about that, minus after. Or we could do after minus, I can't type the word before. All right, there we go. And the question is we want to know is what would a negative number indicate in that sense? So a negative number here would mean that after is the larger number. Now, if after is the larger of the two numbers, what does that mean? Well, remember, a bigger number means more pain, right? So this would mean that the pain increased. That hypnotism made the pain increase. Now here we can say a negative would mean that before was the larger number. So what would before being a larger number mean? Well, if I'm more pain, if I have a larger number, if I'm in more pain before the hypnotism, that means that the hypnotism had less pain. This means this would mean that the pain decreased. Now, notice that they're saying the same thing, right? Doesn't really matter. Just do you want a negative to showcase pain increase, or do you want a negative to showcase pain decrease? It's really up to you. If you go back and you reread this, it did not tell you which way to do it. And so you have to make a decision here. Personally, I think that we're looking for a decrease in pain, that's supposed to be a nice positive thing. And so I would like to associate that with the positive number. So a pain increase is something that we don't want to have. So for me, I'm going to write before minus after. And the reason that I want to do this, that I should go through and do this before I actually do any subtraction, is that I want to, when I get my numbers, when I've done my subtraction, I want to look at it and say, well, what the heck does that mean, right? So what I'm going to go through is I'm going to say equals, and I'm going to go before minus the after. I'm going to hit enter. So this person had a negative number, and if we look, we can see 6.6 to 6.8, they did actually have an increase. So let's go ahead. And there we go. So I just dragged it across. And now this is the data that I am actually going to do all of my testing on. This is the data that's going to tell me what to do. So I need to find my mean. And we're going to go ahead and say equals average. And this is the data that we want the average of. So we had a positive number, that means decrease. So there was an average decrease of 3.125 across our subjects. Let's go ahead and get a standard deviation. That's our little s, right? So I'm going to call it little s. So equals stdev. Make sure you're doing stdev and not one of the other ones. Go ahead and highlight it. There you go. So our standard deviation here is about 2.9, 2.911. And then we need the sample size. So we need our n. And you can, if you have a larger set and you don't want to count it, you can hit count. Ooh, C-O, count. And you can drag across to count. Make sure you don't include the B minus A in any of this or you'll be sad. So here we go. Now remember, paired mean data is weird because you're going to go here, you're going to look in here, you're going to look on your TI and you're going to say, I don't see the paired mean. Where's the test for a difference of paired means? It's because you're going to actually run a t-test. The difference between the paired mean data and a regular single mean test is all of this, doing that physical subtraction and calculating the data off of this one single column. And now once I've done that, right, that's it. That's all. This is all of it. This is what I need to, these are my statistics that I need to run stuff off of. So we're going to go ahead and copy this. So we want to do a test of a single mean. We're going to throw that in there, and then we're going to copy this, and we're going to throw that in there. Now it took my S really far, which is great. And we're going to copy our N in there, because you don't want to, and now notice that it did cut me off, and that's fine, but I don't want to round too early. Notice how things are going to change if I start rounding this S. Ooh, do you see those numbers change? Right? I want to be a little bit careful. If you round your standard deviation too early, or if you round your standard deviation, that's going to round everything else off, and it might throw you off. Now, again, what am I plucking out of here? There's the mean that I put in. There's the S that I put in. There's the standard error that I put in. There's my N. There's my degrees of freedom. I didn't set up any of this part. This is actually not fully right. So I need to go back. What is the test asking? Because it's a difference of means, my null hypothesis has to be 0. We're testing, was there a change, right? If there's a change, then it should be negative or positive. If there's not a change, it's 0. So we're testing at 0. Now, what are we testing for? We are testing to see if it's lower after hypnotism. That is this the smaller number? Well, with the way I subtracted, a negative would be a smaller number, right? So a negative makes a smaller number, or my before makes a bigger number. So I want to know if these are positive, right? That's what I'm looking for. Is my average a smaller number means a positive number? That's what we should say. So the after is smaller implies a positive value. So I'm looking for positive values, which means I'm doing a left-tailed test again. Now, if we'd wanted to, we could have done it this way, a right-tailed test, but then we would have needed to work with the after minus the before. So we're doing a right-tailed test again. All right, we've got everything set up. You can see your mean, you can see your standard deviation, you can see your sample size. This calculates the standard error for you right here. It calculates your degrees of freedom for you right here. It calculates your t-value, which is the test statistic, and it calculates that p-value for you right here. All right, and that's all I had to show you. I hope this helps out.